Everyone. It's my pleasure to introduce Paul Hand, who will tell us about signal recovery with generative priors.
Thank you so much for the invitation to speak. I know there was a talk earlier today by Bruno on a very similar topic, so hopefully I'll be able to share some other perspectives on similar questions. I'll try to make this talk as self-contained as possible, since I know the video of this is going online. And so here we'll talk about signal recovery from generative priors just to set the stage. The idea here is you have an image, let's call it x naught. You have some measurements of that image. Let's call those phi of x naught. And depending on the actual applied problem of interest, you might have a different structure of phi. So you might want to solve denoising, where phi is really like the identity plus noise, or you might want to in-paint missing pixels, where phi is really just a subsampling of the image, or do super resolution or compressed sensing. Or in this talk, I'll focus a lot on phase retrieval. And so there, the problem is to recover x naught from phaseless linear measurements of it. Right. So I want to do the quick reminder of what the story was for sort of like plain compressed sensing, because this is going to set the stage for the sort of result, the sort of like rigorous result we want to prove when we talk about generative modeling. But let's remember that so there is this standard prior for modeling images, which is a sparsity prior. So in a particularly chosen basis, an image might be modeled as having relatively few non-zero coefficients, right? And so if we tuck those coefficients into the vector x, we might want to find the coefficients x such that the measurements of those coefficients are what we observed. And here, this problem is NP hard. And so there's the standard convex relaxation to, instead of minimizing what's called the L0 norm, the number of non-zero coefficients, we'll minimize the L1 norm. Right, so this led to sort of like very significant like mathematical advance, where from like Candace, Romberg, and Tao, and also David Donahoe, studying the case of, say, a k-sparse vector. The question is, how many measurements do you need to recover that k-sparse vector? If your measurements are random and you have like k log n of them, where n is the dimension of your ambient space, then you can solve this linear program in order to find them, right? So this is the celebrated result that, like, with high probability under a random measurement, random linear measurement model, you can recover, in essence, a k-dimensional signal from roughly k measurements. All right, so I put this on the screen because this is the sort of result that we're going to want to mirror when we talk about generative models. Right. So there's a challenge with this view. So like I said, the sparsity perspective is very celebrated. It, in the case of linear measurements, allowed for recovery at the sample complexity that you would expect, right? Proportional to the sparsity of the signal. Right, but unfortunately, this doesn't appear to be working in the case of certain nonlinear problems. Right, so the nonlinear problem I want to focus on is this compressive phase retrieval problem, and here the problem is as follows. Right, you have some signal x naught. You have a matrix A. A is compressive, so it has fewer rows than columns, and you're given an absolute value of ax naught. From that, you're trying to find x naught. And you're trying to impose this sparsity prior, right? So M should be more than K or more than S if it's an S-sparse system, and you're trying to recover the signal. So the problem here is that this is an open problem still, that there's no known efficient algorithm to recover an S-sparse X naught from order of S generic measurements. Now I have to remind us that, like, by generic, right, that this means essentially like random. Right, so if you have non-generic measurements, if you like cook up this matrix A to have this exact structure that factors in a particular way, then you can indeed get optimal sample complexity for solving compressive phase retrieval in that case. But in the generic case where these measurements are not really structured to make your life easy, then this problem is still hard. Right, so this problem has been attacked by many very smart mathematicians. And the perspective of this talk is going to say to back up for a second, right? So compressive phase retrieval is the task that one might be interested in application. And what that means is you're a scientist, you're imaging some signal, like maybe a protein or something, you believe that that protein is low dimensional in a certain way, how can you take only as many measurements as the complexity of that like model that you have? Right, so there's no reason why this has to be sparsity, right? It just happens that images happen to be frequently modeled as sparse in particular bases, which are chosen by people. So if we can pull the people out of the loop, if we can start looking at this from like a data-driven perspective, then perhaps we can do better. So in essence, what's happening is we're saying, like, here is this hard problem, but the hard problem isn't actually what we want to solve in practice. So let's find a different approach to sidestep the hardness, right? And so that approach, we'll talk about in a minute. But what I want to also point out is that in some cases you can even like prove that you can't use standard techniques to get sparsity to work, right? So here, this is an example of a convex program. Something this would be called Sparse PhaseLift. So the idea of PhaseLift is you have these phaseless measurements of a signal. If you lift those to be measurements of a matrix, they become linear measurements. And so then you're looking for a low rank matrix given the measurements that you have. And so if you could envision that you could impose a sparsity prior on that matrix, that's the matrix's coefficients, and then try to recover the matrix and then do a factorization of that matrix. And unfortunately, like Xiaodong Li and Vlad Vorninsky proved a while ago that like problems of this form like provably cannot work at finding an optimal, at finding the sparse signal at optimal sample complexity. Right, so here we have the setup. There's no known algorithm, and for some very natural types of algorithms, you can prove that they don't work. Right, so this is why we're sort of sidestepping this approach. Right, so that sidestepping comes from like recent data-driven advances from the fields of artificial intelligence, in particular deep learning. This was on the front page of the New York Times in 2018, and so here, this is there are AI-based algorithms that can be shown a large data set of natural images. They can, in essence, learn the distribution that data set came from in order to sample from it. And so that is what a generative model is. And they've been trained for all sorts of applications. And for example, they can give you like high resolution photorealistic images of human faces. You could also train them in biological cells, MRI images, you name it. All right, so like the mathematical structure of these are actually like quite varied. It's hard to put them all in a bin, but some of them have the flavor of a mapping that is learned. So here you're given samples in, let's say, Rn. So these are like images, n is the number of pixels essentially. And you're assuming that those are coming from some probability distribution, which you don't know in advance. And your goal is to learn these. Right, so you're going to model this distribution as the push forward of a simple distribution under a learned function. So that simple distribution we might say this is a Z. It follows a standard Gaussian in k-dimensional space. You have some map G, which maps k-dimensional space to n-dimensional space. And here k could be less than n, k could be equal to n, and there are successful examples of both of these. Right. So just to give you an example, like what does this look like visually? Like here you might have, say, like this latent space on the right, that's that k-dimensional space. The image, you should think of the data space as that's like image space. So each of these like blue points on the left, those are like separate images. Right. And so then your distribution might be multimodal, right? You might have like cats and you might have dogs. And then in the set of images, there might be some complicated geometry between them. So here you might sample a Z that's random, like one of these red pixels down here, push it through this function, you get a new image that's from that distribution. And so that is if everything goes well in the training of your generative model, right? So now, supposing that you have these models, right? How do you use them in practice? Well, first you need to train them, right? And so this is a question for computer scientists. Right? What architecture do you use? Like what sort of neural network do you use? If you're even using, well, I don't know. And so then here you're going to learn this neural net, which is going to perhaps take random noise as input and output new samples from this distribution, maybe this distribution of images of flowers. So once you have that G, then you can give that to the practitioner, and they're going to have some measurements. They're going to have some measurements which is presumed to be like phi of x naught for some unknown x naught. And then you can write down just a straightforward minimization problem, find this latent code z such that g of z, when applied under the measurements phi, agrees with the measurements that you have. And this problem you could solve, for example, using gradient descent. Right? So in a sense, this is sort of the most immediate thing you would try with the most immediate method. And the field of deep learning is full of all sorts of tips and tricks for like how to train these models, how to do that optimization. Maybe you're not using exactly gradient descent, maybe you're using fancy variations of it, but you can use ideas of that flavor. And so then you can use these to do compressed sensing. This result was famously studied by this Bora, Jalal, Price, and Demarcus paper out at UT. And here, their approach for compressed sensing was, right, take this G, which is trained. You have some image X naught, which is either in the range of G or near the range of G. You have measurements A of X naught. If you can go find the Z naught that corresponds to that, then you have essentially found your image. You can push that back forward through G, you get an estimate of your image. And so then they studied this optimization problem. Right? And so they showed that this can succeed with significantly fewer measurements than sparsity-based approaches. And they introduced some theory that showed that if you can solve this optimization problem, then under certain conditions, then you can recover the image that you're looking for or an estimate of it with on the order of k measurements. Right? So what I'm going to talk about, or what I'm talking about in this talk is the phase retrieval problem. And so just to compare this is the same as what we just saw on the last slide, but where you have these like absolute value of A of X naught as the measurements. And so then that modifies this optimization problem in sort of an immediate way. Now I'll comment like it's not trivial to just write down that formulation. You can envision squaring the terms inside or something like that, and you actually get different artifacts and sort of a different method that has that might be easier or harder to analyze. Right, so I want to show like a picture of what's really going on here, because this is also going to allow us to compare these methods to sparsity-based methods. All right, so let's think I have the set of all images. That's like the ambient space here. Then I might have the set of natural images, and that will be some low dimensional manifold in this space. But then I might have a further subset of natural images of a particular class that I'm interested in. For example, MRI images. Right? And so then that might be represented by, say, like this red curve, or in this case, it's sort of a picture of a train. Right? And so then here, you're given measurements of your signals. So that is to say there's some, like in the linear case, there's some like affine space that you're on. And so the question is, where does this intersect this manifold? Does it intersect it at like exactly one point? And if so, then that's your signal estimate. Okay. So like already this picture shows a potential improvement of these generative models over sparsity-based thinking. And that is the dimensionality of your natural signal class like really comes into play. Right, so here, if we think of this image, right, and sort of like the obvious like neighbors of this image, like here's one train going down this track, right? How complex is this set? And it would be natural to model that set as one dimensional, right? It's just where along that train, where along those tracks is that train? So if I was able to, train a function which took R1 to that set of images, right, then I should expect to be able to recover any particular image in that set with one measurement. However, if I take like a wavelet perspective where I say like, oh, well, this is a complicated image, I'm going to represent it in a wavelet basis and study which coefficients are non-zero, then I'm going to have many, many more than one, O of 1 measurements that are non-zero. Right, so this shows a potential benefit, which is that when you have a signal class which is itself relatively low dimensional, that class could be lower dimensional than the representation in this particular wavelet basis or Fourier basis, right? So that's one source of a way to improve over like sparsity-based approaches. Right. So, but this is, I mean, I want to get to one of our like rigorous results since this is a more theoretically inclined group, right? And so my comment is, right, these generative priors do allow for rigorous recovery guarantees at optimal sample complexity in K. So I want to think about this model briefly, right? So this is meant to be a model of a GAN, a generative adversarial network, which in this case is taking a low dimensional input into a high dimensional output. And that, that is only one type of generative model that exists out in the world. Sometimes K equals N, and then it's a very different story. But this GAN is going to be modeled as a feed-forward, fully connected neural network with no bias terms, which is represented in this form, where you take your input Z. Remember, that's low dimensional. You hit it with some dense matrix W1 that increases the dimension. Then you hit that with a rectified linear unit. What that means is you take the positive part and you kill any negative parts component-wise. And then you just have many layers of this operation, where you have a linear operation and then a nonlinear activation function applied to it. This is, morally speaking, the essence of what a neural network is without what are called bias terms. And so we're going to study, like, we want to study a model of this so that we can make solid claims. And that model is going to be, we're going to assume that at each layer, there are more neurons than in the previous layer. So that is to say, there's an expansivity condition, like Ni is bigger than Ni minus 1. In our work, that we're going to assume that it's bigger than some constant times Ni minus 1 with a log factor. So we're also going to assume that the values of these weights and the values of the measurement matrix at the end are all Gaussian. Right? So this really is just an assumption for like initial theoretical convenience, but there are some like reasonable motivations for why it would make sense. Right? So when you train a neural network, you initially start at like random weights, and then you optimize them to fit the data set that you're training them on. Now, it turns out that in a highly over-parameterized regime, there are certain cases where the weights don't actually change that much. And so then what the initially random weights are often close to being random at the end of the training process. Right? So, and this is part of the state of like the theoretical understanding of when can neural nets even be trained. Right? And there are also other studies that show that if you look at the statistics of certain trained nets, then you get very Gaussian-like behavior in them. Right. So anyway, there's reasons to model it this way, it does allow us to make sort of like a rigorous claim. Right. So this is a theorem that we introduced. So with my graduate student Oscar Leong, who's now going to be a postdoc at Caltech this fall, and then with Vlad Vorninsky, who is the CEO of a self-driving car startup called Helm. And what we showed was that this generative model, right, this random model of a generative model allows for signal recovery from nonlinear compressive phaseless measurements at optimal sample complexity. So that is to say, if the number of measurements scales like K, where I'm ignoring all of the log factors, dependence on D, and various other things, various other terms in the problem, if the network layers are sufficiently expansive and if everything in the problem is Gaussian, so the weights, the measurement matrices, et cetera, then this function actually has like a very nice landscape that can be optimized. Yeah, is there a question?
Yeah, is the network itself given?
So the question is the network itself given? In this case, yes. So the network is modeled to be a sample from just a sample of Gaussians in all of the entries of the weight matrices W and the sensing matrix A. And then you're saying that is now fixed and handed to you.
That's given to the algorithm.
Yeah, so that's given to the algorithm as it would be in practice.
I mean, I'm unclear if it would be in practice in the sense that you're assuming that it would be learned to a high degree of accuracy in practice.
Right. So in practice, you would take you would take data, you would train a generative model G, then you would hand that G to someone who's doing the inverse problem. And for the person who's doing the inverse problem, that G is fixed.
Okay.
Right. So here the theory is, I mean, this gets to like a very deep question, right? Like we don't know, and I'm not sure anyone knows, like how to mathematically describe like natural data. Right? So like all of the theoretical results in this area are going to have the form where they sidestep the question of what does natural data really look like? And they're going to say, okay, assuming the structure of what it could be, then here's the result that we have. Right? So here we're assuming for the inversion G is fixed. We're assuming it was handed to you as the outcome of just a random process. And then for the inversion, that G is the G. So now the model for what a natural image is something that's near the range of that random function.
Perfect, thank you.
So here the comment is that the optimization problem that we wrote down on the previous slide actually is relatively nice in this situation. It's not convex, like as you can see, but it has so a very nice structure that if you run gradient descent down it, maybe you get stuck at this left well, but the global minimum is at the right well. This is really a plot versus the latent dimension, the latent variable z, in the case of dimensionality equals 2. And so there's some tricks that you can do to make sure that you don't get stuck in this spurious minimum. So we showed that this function is like able to be optimized, and in fact, there's so follow-up work to this that we proved that gradient descent with a minor twist can actually provably converge to the global minimum here. All right. So I mean, I'm running a little low on time, but I just want to quickly comment that sort of the bread and butter of this proof is based on like discontinuous matrix valued random functions, right? And so here you want to study matrices that have this form, like you have like random vectors wi, so you want to study like wi transpose, so something like a Wishart matrix. But remember that the neural net itself had these RailU activation functions. So they kept positive terms and sort of zeroed out negative terms. So here this Wishart matrix is going to be have these extra terms where there's like an indicator function for whether this random direction wi is aligned with some direction y or some direction x, and we want to study this as a function of x and y. Right, so this is a discontinuous function of w. It's a random object, and we want to show that it concentrates toward its expectation. And so we can prove things like this, with high probability. Then if like this matrix is like taller than it is wide by like n log n factor, then we can get this concentration. So this result has actually been improved by others. But it illustrates the type of mathematics that's underlying this like non-asymptotic result. This result works in some like practical situations where you can like train a generative model, in this case on digits, and then with many fewer digits, you can recover the digits somewhat accurately relative to these sparsity-based approaches. So this second row is this deep phase retrieval approach with something called the variational autoencoders, the generative model, and it was able to succeed where all these, where this, say, sparsity-based method did not. And so I want to sort of get to this last like qualitative point. Right, so this is a plot of like reconstruction error versus number of measurements for phase retrieval under a variety of signal priors. So this blue curve is our work with using generative models. This and these other approaches are like other like sparsity-based approaches for phase retrieval. And so what we see is that at the low measurement regime, like we can get significantly less reconstruction error than these sparsity-based approaches. But at the high measurement regime, like the performance of these generative models often bottoms out. And then the sparsity-based models can perform well in those regimes. And I want to just sort of like visually reveal why this is the case. Right? So you could say like, I'm going to give you a bunch of faces. And I'm going to train a generative model of those faces. So maybe I give you celebrity faces. There's a standard data set called celeb from which you can train a generative model. And then I'm going to take non-celebrities and I put them through, ask like, what is the closest function in the range of my generative model to those faces? And here, these faces on the top, get turned into these faces on the bottom, and you can see there are significant errors that happen. For example, like this older woman becomes a younger woman, because the training data set like is biased toward youth. And there are other biases, away from glasses and beards. There are biases toward various skin tones, et cetera. You can take this to, so the comment is these can have like significant representation errors. Like they might not be able to represent your signal. Right? You trained it on some data, that data might not be close to what you're testing it on. We can take this to like an extreme. Remember, we train this model on faces. Let's start giving it progressively less face-like things, like this chimpanzee, and then it's going to round it to perhaps the nearest human, which is someone whose eye sockets are exactly the same, or whose glasses are exactly the same size as the eyes of that chimpanzee. And you can see how, in a sense, this generative model is doing what we asked it to do, right? It learned what humans are. We gave it something. It gave us the closest thing toward what we got. Even here, like this door gets turned into a face, or this butterfly gets turned into a face. Right? So you can indeed have very poor out of distribution performance. And this is a problem because when you're thinking about, why are we doing all this? Like we're building systems so that we can image things. Maybe we're imaging like new medical pathologies or something. So those are precisely going to be things in some cases that we have not seen before, and they're going to be out of distribution, right? So this failure of being able to handle things that are out of distribution is a significant issue. And it's something that there's been a lot of work in the field about. So this really is just, in essence, the background to then point out that there's now been significant follow-up and a variety of approaches for how you handle the representation error of these generative models. All right, so just to kind of tie some big ideas from this talk. So generative priors can, in some cases, be optimally exploited for nonlinear problems. Right? So that means if I have a generative model that describes my system as a k-dimensional manifold, then I should only have to pay k measurements in order to recover a point on that manifold. Right? So this is good. So further, the added benefit is that it's possible that the dimensionality of that manifold is less than what it would be had you used sparsity priors. Right? So even if we could optimize sparsity linearly, it could still be worse than generative modeling. So the trade-off here is you get a low dimensional non-convex optimization problem instead of a high dimensional convex program. And then this last comment, that in some cases, generative priors can empirically outperform sparsity priors for a variety of problems. I want to end on this sort of a little bit as a reflection and a little bit as a word of caution, right? So generative models, as we've seen, have some of these very nice properties, right? We can exploit them optimally, like we saw before, but there are issues, right? Let's remember, a generative model didn't just appear from the sky, right? It was trained on data. So if you're solving a problem with a very specific domain where you don't have a lot of data, then a generative model might not be for you. Right? Now, there are fields of machine learning, such as transfer learning, where maybe you can train elsewhere and fine tune in your domain, and there are tricks that you can do, right? But that's one point. The other point is that there are entirely other approaches which don't require any training data whatsoever and are based on neural networks. And so these are things like something called the deep image prior and the deep decoder, where you have zero training data, yet you're exploiting some of the bias of neural networks itself to help you recover images. And those methods work surprisingly well, given that they have no training data, right? So one should not rush to solve problems with generative modeling, but there are many cases where generative modeling have showed a very nice performance in practical applications. All right, and with that, here's some references. One thing I do want to point out is we are running a workshop at NeurIPS this winter on deep learning and inverse problems. And so if you're interested in attending that or submitting a paper to that, I encourage you to look it up. All right, thank you.
Great, any questions? Maybe Cindy, you want to start getting set up in the meantime?
So it sounded like just earlier the last claim was that this floor in the error of this recovery using a generative
prior, I guess, was because of kind of a mismatch between the generative model and what you're testing on. Is that right?
Well, I would say that in that particular case, it is because you might be using a generative model with a finite dimensional representation of the data. Right, so you'll be an image space and you say like, I'm modeling faces as 200 dimensional. But like faces might actually be 250 dimensions. And so now there's 50 dimensions you're not covering. Right, and so that's going to mean that you're just not going to be able to model those dimensions. So these approaches that are working that don't have a significant of a representation error problem are ones which might say maintain a probability density over all possible images. And then they allow you to like gracefully have a tail of, like how natural things are. So it really goes back to like the choice of structure that you use for your generative model, like can cause problems. The more recent methods are ones that are much higher dimensional in representation. Now, the problem with that introduces now a theoretical problem, right? Ultimately all of this theory that I showed today says if you have a k-dimensional manifold, you need k measurements to find a point, right? But in practice, people aren't using low k-dimensional manifolds anymore. People are using high-dimensional manifolds, sometimes with more parameters than the entire dimensionality of the problem you have. So now this theory just doesn't apply, right? So that's sort of it's a theoretically very motivating issue based on what's going on in practice.
But sorry, just to follow, why don't we see the same phenomenon in the sparse kind of variants of it? Like, shouldn't there be something similar where, you know, the true images or whatever aren't sparse in the wavelet basis or something, and therefore we should also see some baseline?
Well, and I mean, so there are always like parameters that are tuned. And so then you can like in a case where, like if I say, I give you like all of the pixels of the image, right? And I say like, find the sparsest thing that's consistent with that. Well, that's a singleton, right? Whereas in the generative model case, you could say, find me the point in the range of the generative model that's closest to that. Now you have an error.
Okay, great. So let's thank Paul again.
Thanks. Yeah.